This is lecture number 23 of high performance computing. In the previous lecture we had looked at some of the problems that could arise in a pipeline. A pipeline is an implementation of a processor or a piece of hardware to execute instructions, in which in the case of the pipeline processor, the design objective is to make the throughput or the rate of execution of instructions faster than they would have been in a non-pipeline processor, by using the different pieces of hardware in some kind of an overlap mode to the extent possible. Now we had looked at we took an introductory view on the different kinds of hazardous situations that could arise in a pipeline in the previous lecture, and had seen that there are a class of hazardous situations called structural hazards, which can be handled by, for the most part, by appropriate design of the pipeline, by making sure that the resources of the pipeline are designed in such a way that they can be used by as many instructions as may need them at the same time. And we were then starting to look at the data hazard, which is a situation where an instruction in the pipeline requires a result or a piece of data which is in computation or being produced by an instruction which is ahead of it in the pipeline. And we were looking at the simple example of an add instruction which has R3 as its destination and is followed by a subtract instruction which has register R3 as one of its sources. And the problem as we saw it was, we know that based on our definition of what happens in each of the 5 pipeline stages, I refer to IF, ID, EX, MEM, WB as the 5 stages of the pipeline. So we know at what point in time instruction I writes the result into register R3. We also know at what point in time instruction I plus 1 reads its operand, its source operand from register R3. For example, we know that the updating of register R3 as far as instruction I is concerned happens in cycle number 5, and we know that the reading of register R3 by instruction I plus 1 happens in cycle number 3, and therefore instruction I plus 1 is reading its source operand before instruction I has actually written the value that is supposed to be used, and hence the designation of this as a hazardous situation, a situation in which unless the pipeline is corrected or unless something is done, the result of executing simple program instruction sequences like this would be wrong. In this particular case, the instruction I plus 1, the subtract instruction, would get an old value, the previous value from register R3. Right now, based on our analogy from petroleum pipelines, we realized that one way that this hazardous situation could be handled is essentially by preventing instruction I plus 1 from reading its operands in cycle number 3. In other words, if instead of allowing instruction I plus 1 to use the ID hardware in cycle number 3, I pump a bubble of air into the pipeline, and that bubble of air will progress through the pipeline in subsequent cycles. Now the question that arises is it safe for instruction I plus 1, the subtract instruction, to read its operand in cycle 4? So by pumping one bubble of air into the pipeline, in other words, by delaying instruction I plus 1 by one cycle, I have prevented it from reading the old value of register R3 in cycle number 3. But now it will go to the ID stage in cycle number 4, and the question is it safe for instruction I plus 1 to read its operand R3 out of memory, out of the register file in cycle number 4? And the answer is no, that's still too early. Therefore, I actually need to delay instruction I plus 1 by another cycle. So after the first bubble of air, another bubble of air must be inserted into the pipeline. In other words, it looks like instruction I plus 1 must be delayed by the next cycle as well. What about the cycle following this? Is it safe for instruction I plus 1 to read register R3 in cycle number 5? In other words, is it safe for the subtract instruction to go to the ID stage in cycle number 5? And the answer is we could make it safe for the subtract instruction I plus 1, to read its operand in cycle number 5 if we designed the write back stage and the ID stage hardware in such a way that the updating of register 3 happened early in the cycle and the reading of the register R3 in the ID stage happens late in the cycle. Remember, I suggested that we're not going to look at the details of what happens within any one clock cycle, but this is an exception, because it should be possible for us to think of designing the hardware in such a way that within that cycle number 5, it is guaranteed that the write back will happen early in the cycle and the reading will happen late in the cycle, and that therefore it would be safe for us to assume that the instruction I plus 1 could be allowed to use the ID hardware in cycle number 5. So this is something that the hardware designer would have to guarantee, but it's something which for the moment we assume that can be done. It doesn't sound unachievable. So with this assumption that in the write back stage the updating of the register happens early, and in the ID stage the reading of the register file happens late, so with this assumption we can actually allow the subtract instruction to use the ID hardware in cycle number 5. Subsequently it will do the subtraction in cycle number 6. It will occupy the MEM hardware without actually doing any relevant activity in cycle number 7, and will write its destination register R4 in cycle number 8. In other words, with the penalty of having 2 cycles, cycle 6 and cycle 7, in which no instruction completes, we could actually handle this data hazard situation. Note that an instruction I completed in cycle number 5, after that instruction I plus 1 completed in cycle number 8, which means that there were 2 cycles when no instruction completed, which is something which we would like to avoid. Therefore, this is not our first choice as far as the solution to the data hazard is concerned. So just note that what we are talking about here is delaying the progress of instruction I plus 1 through the pipeline. That was the suggested solution. Okay, now the question which will arise in your mind is, this delaying of instruction I plus 1 is obviously not going to be done by the programmer. The programmer is just writing a program, or the compiler. The compiler is just generating the machine instructions. Who therefore is doing the delaying of instruction I plus 1? The answer is, this is clearly something that has to be done by the hardware. It must be something that is built into the pipeline. Therefore, there must be hardware within the pipeline which can identify that this is a situation where there is a need to delay an instruction. Now the idea here is that we are delaying, and a more technical term for this kind of delaying is to refer to it as stalling, S-T-A-L-L. And this is a verb, so we could talk, rather than talking about delaying an instruction, we will talk about stalling an instruction. And the idea here was that we needed to stall or delay the progress of instruction I plus 1 through the pipeline, in this particular case, preventing it from using the ID hardware for 2 cycles. Only then was it safe for it to read the register R3 and get the right result in terms of what the instruction I was supposed to generate. So we will henceforth use the term stalling an instruction. Now, I just mentioned that the decision whether or not to stall an instruction is not a programmer decision, it's not a compiler decision. Very clearly it's a hardware decision. So there must be a piece of hardware that decides whether or not to delay an instruction in its progress through the pipeline. Such a piece of hardware is known as an interlock. Right? So interlock is a term used for a piece of hardware that is included in the pipeline or in the processor. The purpose of this piece of hardware is to detect such data dependencies and to implement the stalling of the dependent instruction. Now I'm numbering this as one possible solution to data hazards, so very clearly we're going to see others. Let's think a little bit about how complicated this interlock hardware might have to be. You'll note that the situation that we had was, there was the add instruction and there was the subtract instruction. This was instruction I, this was instruction I plus 1. So how will the interlock hardware detect that there is a problem here? The interlock hardware would have been able to detect the problem, the data hazard, by noting that one of the source registers of instruction I plus 1 is the same as the destination register of instruction I. And therefore, by comparing the source register identifier of instruction I plus 1 with the destination register identifier of instruction I, in other words with a very simple comparator, it is possible for the interlock to identify such situations. Obviously, it will have to compare not only the first source operand but also the second source operand, therefore 2 comparators and possibly more, but some number of comparators are what would be required. A comparator is a piece of hardware which can compare 2 things and see if they are the same. So it's just checking to see if the first source operand of instruction I plus 1, which is one of the bit fields within the instruction itself. You remember the instruction format. So it's comparing that bit field with the destination operand bit field in instruction I. So just comparing a few sequences of bits is what is involved in this interlock hardware. So it's not a very complicated piece of hardware. It does a number of comparisons of that kind. So if it does find out that there is this kind of a dependence between instructions, then it basically has to cause the dependent instruction to be delayed and have a mechanism for, rather than allowing the instruction to proceed through the pipeline, cause non-activity or a bubble to proceed through the pipeline. And so people do talk about pipeline bubbles. The term bubble was possibly motivated by the idea of pumping air into a petroleum pipeline, but is commonly used in pipeline discussions today, talking about stalling a pipeline or inserting a bubble into a pipeline. So the situation as we have it, if I look at what's happening with the timeline and I look at the different instructions, is that the add instruction goes through, here the cycles are numbered from 0 through 4. Note that it doesn't really matter how we number the cycles, but the add instruction goes from IF to ID, EX, MEM right back in consecutive cycles, is followed by the subtract instruction, which got fetched in time, but then had to be stalled by 2 cycles before it could be decoded. So this is a slightly more concise notation than the previous notation we were using with the diagrams, colored boxes, and I may sometimes use notation like this, since we now understand pretty much what the content, the intent in having the colored diagrams is. So the same information is contained in this kind of a diagram. So we notice that the subtract instruction is, if delayed by 2 cycles, results in safe updating of register R3 as well as reading of register R3, the update happening at the beginning of cycle 4 and the reading happening at the end of cycle 4. Okay, now the question which now arises is, what if the next instruction, we have to worry about the next instruction. Let's suppose that the next instruction also requires use of R3. And the question that arises is, what about the next instruction? Now, if we think about the next instruction, this can be left out, but if you think about the next instruction, conceivably the OR instruction could have been fetched in cycle number 2, but unfortunately the fetch hardware is still not available for use, since the fetch hardware is still being occupied by the subtract instruction. When we say that the subtract instruction is stalled, we meant that it was prevented from entering the ID hardware, which means that it must still be occupying the IF hardware, which means that it's not possible for the OR instruction to be fetched in cycle number 2. So the OR instruction starts life by being delayed by a cycle, but we could argue that it could be fetched in the next cycle if the buffering between the IF stage and the ID stage, I had shown the buffers, the storage between the IF stage and the ID stage is appropriate. So this is what one could argue, but one sees that if one did allow the OR instruction to be fetched in cycle number 3, then it would require the ID hardware in cycle number 4, which would amount to a structural hazard, and therefore one does have to stall the OR instruction for one more cycle. Therefore, as far as the OR instruction is concerned, the earliest that it could be fetched would be cycle number 4, followed by being decoded in cycle number 5, etc. Now the question that arises at this point in time is, what if the OR instruction also uses as its source operand register R3? Remember that R3 is the destination of the add instruction. Is it safe to allow the OR instruction to just go through the pipeline, or will it also have to be delayed further as far as entering the ID stage is concerned? We notice that the assumption about the point in time at which the add instruction updates the pipeline, updates the register file, was that the add instruction updates register R3 in cycle number 4, and therefore it's obviously safe for the OR instruction to read the register file in cycle number 5. Therefore there's no problem as far as the OR instruction is concerned, even if it has the same source operand register R3. So to summarize, the first idea that we have seen is that the pipeline designer can identify situations where there could be data dependence between instructions and build special hardware using simple very simple comparator circuits, to detect situations where there are instructions in fact which have a data dependence between them, and in such situations take the action of stalling the dependent instruction. In our example, the later instruction had to be stalled for 2 cycles. Okay, now let's go back to our pictorial diagram and see what the situation is. Here we have pretty much the same problem as in the previous. Some of the instruction labels are a little bit different. Here once again the add instruction has as its destination R3 and the subtract instruction has as its source R3, so there is a data dependence. Now the question which we're now going to think about is the following. Let's follow the fate of the add instruction through the pipeline. Here once again we're showing the timeline progressing in this direction. Okay, now the add instruction is fetched in the IF. It is decoded in ID. In other words, it reads its operands R1 and R2 in ID, and it does the addition of the values in the EX stage. Now the reason that we are particularly interested in that observation is that what this means is that at the end of the EX stage, the result which is ultimately going to go into register R3 has actually been computed. You'll remember that the result is the result of adding the contents of register R1 to the result of R2, and that happens in the ALU during the EX stage of the add instruction, and therefore by the end of the EX stage of the add instruction, the value which is going to go into register R3 is known. It is available. In fact, it is available in a special purpose register which we refer to as ALU out at the time that we were looking into the innards of the different pieces of hardware. So subsequently we understand that the actual value which is computed and available in ALU out at this point in time will be written into register R3 in the early parts of the write back stage of the add instruction. However, it is available in ALU out as early as this point in time, if I look at the timeline. Now the next question that we could ask is, when does the subtract instruction actually require that value? And the problem that we have is that the subtract instruction by default, if I assume that the add instruction goes through the pipeline in cycles 1, 2, 3, 4 and 5, the subtract instruction, if it just follows the add instruction, would have gone through the IF stage in cycle 2, the ID stage in cycle 3, the EX stage in cycle 4 and the MEM stage in cycle 5, and write back stage in cycle 6, if it had just followed the subtract instruction. Okay, now and that would have been a problem, because in the ID stage it would have read the value, it would have tried to read the value from register R3 towards the end of the ID stage, which is before the value has actually become available, which is only at the end of that cycle. But we ask another question. We ask the question, when is the result of the previous instruction actually required by the subtract instruction? And if one thinks about it a little bit, one realizes that the subtract instruction is actually doing the subtraction only within the EX stage. That's where the ALU must have at its input the value that we are talking about over here. In order to subtract R3 minus R4 in the ALU stage, the subtract instruction is supposed to subtract R3 minus R4. In order to do that, it must have at its ALU inputs the values from register R3 and from register R4. And you notice that this is a point in time after the point in time at which the desired value is actually available in the register called ALU out. In other words, it looks like there's scope here for avoiding stalling an instruction, because the desired value is actually available somewhere in the processor before it is actually required for doing the subtraction. And therefore, if one could find a way of routing the desired value from ALU output to the place where, as computed by the add instruction, to the place where the subtract instruction requires its use, then one could avoid having interlocking or stopping, one could avoid delaying and stalling the subtract instruction at all. This is the observation which we could make here, and could result in a new technique for handling data hazards. Now, we may ask, what if both the following instruction after the subtract, which may also be an instruction that uses R3, and we could note that that instruction may have the same problem that the subtract instruction has, because if it was to read its source operands at the end of its ID cycle, that would be well before the add instruction had written the values, the computed value into the register R3. Therefore, both the subtract instruction and the OR instruction suffer from the problem in the current situation. Notice that in this diagram, I have not assumed that the subtract instruction is being delayed at all. In the previous diagram, we had the subtract instruction delayed by 2 cycles, stalled by 2 cycles, which is why the OR instruction was safe to proceed through the pipeline on schedule. In this diagram, we are trying to think of a mechanism through which we can avoid stalling the subtract instruction at all. That's why I started with the assumption that the subtract instruction proceeds through the pipeline just following the add instruction. And the reason for hope was that we saw that the value which is going to go into R3 is actually available for use well before it is needed by either the subtract or the OR instruction. And that therefore, if one could find a way to route it to each of those instructions by some kind of a connection within the processor, within the pipeline, then one could avoid the need for interlocks delaying one completely. Now, this idea of solving data hazards is called forwarding or bypassing, and the general idea is one should find a way in designing the pipeline to forward or to route the result into the EX stage as soon as it is available anywhere in the pipeline. In our particular example, we were able to figure out that the desired result as far as the EX stage was concerned for the add instruction was available at ALU output over here. Therefore, if one could give a routing path from ALU output to the input of the ALU, then one could avoid the data hazard altogether in terms of the need to delay any instruction. So what would this amount to in terms of the implementation of the pipeline? It would require modifying the hardware within the EX stage. What will the modifications look like? Now, I'll just take you back to what the EX stage looked like until now. This is something which we had looked at many lectures ago. So in general, in the EX stage of our simplified pipeline, there is the ALU which does the computation, whether it be for an addition or for a load word instruction. So the ALU stage there would be used for calculating base plus displacement address. It could also be used for a branch instruction, in which case it's used to compute the target PC in terms of PC plus the displacement. But in any event, it takes 2 inputs, the upper input and the lower input. And we saw that there was a possibility that the upper input would have to come from the new program counter, PC plus 4, or from the A register. So NPC, A, B, and IM are the names of special purpose registers which we came up with as we were talking about the design of the hardware for the non-pipeline processor. And then depending on what particular instruction being executed is, this piece of hardware would send either NPC or OR into the upper input of the ALU, and this piece of hardware would send either the contents of the B register or the contents of the immediate register into the lower inputs of the ALU. Okay, now currently what we're talking about is complicating this hardware a little bit more, because there's the possibility that the upper input of the ALU, as in our current example, should not come from the register file at all, because it's been identified that the instruction, such as our subtract instruction, would have to be delayed unless we're able to bypass or short circuit the result which was computed by the add instruction into the input of the ALU. How can one do that? One could do that by actually taking the contents of ALU output and providing a path, in other words a bypass path, from ALU output into that piece of hardware out of which something goes into the upper input of the ALU. Similarly, there's also the possibility that the subtract instruction had not had R3 as its first source operand, but had it as its second source operand, which is why I also show a bypass path or a route from ALU out, which is sort of indicated by somewhere in this region. It's one of the special purpose registers in this region of the pipeline of the processor. So a bypass path from ALU out to each of the possible inputs of the ALU, and modifying this piece of hardware so that in addition to using the decode information about what the instruction is, it also uses information such as that which will be calculated by an interlock hardware. In other words, it computes compares the source registers of the instruction currently being executed with the destination register of the previous instruction. So this piece of hardware will use all that information to route either ALU out from the previous instruction or NPC or the contents of register A into the ALU upper input, and similarly for the ALU lower input. So this requires, as we can see, modification of the processor data path, but not a whole lot of complication. It requires some hardware similar to the interlock hardware in order to decide which of the various possible upper inputs to the ALU should actually be routed to the ALU. So some comparators in addition to the information available from the decode. And conceivably a little bit more complication because there may be other bypass paths that have to be included. As we had seen in the previous diagram, it looks like if one looks at this diagram carefully, the instruction following the subtract instruction may also require the value computed by the add instruction as its source operand, and you'll notice that it's not safe for that instruction to read from the register file because the register file will be updated later, and therefore it too requires a bypass path in order to safely get the value which was computed by the add instruction and not yet put into register R3. So in order to take care of the next instruction, it becomes necessary to include bypass paths from one cycle beyond. Now the way to look at this is, what I'm showing you, what I've added into the diagram is the next stage in the pipeline. Remember that in our pipeline we have the IF stage, the ID stage, the EX stage, the MEM stage, and the write back stage. So the add instruction had progressed, and the diagram which is being shown right now is showing the situation that would have happened if the add instruction was occupying the MEM stage and the subtract instruction was occupying the EX stage, which is why we routed the output from the ALU, which was whatever had been computed by the add instruction, as the input to the ALU from the perspective of the subtract instruction. Now if we are now worried about the OR instruction which follows the subtract instruction, then we realize that at the time that the OR instruction is executed, the add instruction would have moved to the write back stage, the subtract instruction will be in the MEM stage, and the OR instruction will be in the EX stage, and therefore the value of ALU out which is required is not the value of ALU out as computed by the subtract instruction, but the value of ALU out as computed by the add instruction, which will be carried along with the add instruction as it proceeds through the pipeline, and therefore will be available in the buffers associated with the next stage in the pipeline, which is why I will show two more bypass paths going from the next stage in the pipeline to the inputs of the ALU. So let me just clean this diagram up a little bit. So the situation as we have it is that for the simple example that we had, there seems to be a reasonably large number of bypass paths that have to be added into the pipeline in order to take care of the data hazard situation, but the net result will be that there is no need for interlock hardware which will delay instructions. We now have a situation where the data hazards that we have identified will not prevent instructions from proceeding through the pipeline as they should. They just have to be correctly identified by the hardware, and the correct bypass paths will have to be used to make sure that the correct data is used by the instruction. Now this is well and good as long as bypassing or forwarding can handle all possible scenarios of data dependencies. And as it happens, for our simple 5-stage pipeline and our MIPS1 type instruction set, there is at least one situation where forwarding cannot solve the problem, which is what the heading of this slide is going to give away. Forwarding is not always possible. So at least in our example, forwarding is not always possible. And let me show you one situation where the forwarding does not work. Forwarding, remember, is the other term for bypassing. The idea of short-circuiting a value from somewhere else in the pipeline to the input of the ALU in order to allow an instruction to proceed despite the fact that there is a hazardous situation. Okay, now the example that I'm going to construct where forwarding is not going to work is going to be based on the load instruction. So here we have a load word instruction which has as its destination register R3, and recall that when this instruction progresses through the pipeline, it gets fetched, it gets decoded when its source register is read, it executes, at which point its effective address is calculated by subtracting 4 from R1, it accesses the data cache, and finally updates register R3 in cycle number 5. Okay, now let's suppose that the next instruction is a subtract instruction which is dependent on the load word. Notice that it has as its first source operand register R3. It is therefore dependent on the load word instruction. The normal course of events, the subtract instruction will get fetched. It will just follow, the subtract instruction will follow the load word instruction through the pipeline. It gets fetched in cycle 2. It would get decoded in cycle 3. And therefore, in the end of cycle 3, it would read register R3 and R4. We know that register R3 is going to be updated by the load word instruction in the early parts of cycle 5, and therefore if the subtract instruction is to read register R3 in the late parts of cycle 3, then it's going to get the old value. But that was before we learned about bypassing. So we now try to figure out whether it's possible for the value to be bypassed or forwarded from the load word instruction to the subtract instruction so that it becomes available in time for the EX stage to use it. Right? So we're not too concerned that the ID stage and the write back stage, because this was exactly the same situation that we had in our previous example. We just have to understand to what extent the bypassing can be done. So now we need to understand at what point in time, in terms of this this timeline, at what point in time is the value which was read from the cache memory available within the processor for use by the ALU. And if you remember, when we looked at the MEM stage, there was this notion that in the MEM stage the cache memory, the data cache memory will be accessed, and that once that access has happened, the result will become available in a register called, I think, LMD out or something like that. We called it load memory data. There was a special purpose register called LMD, and for all practical purposes the value would be available in LMD at the end of the MEM stage or in cycle number 4. Now, so that tells us when the value is available. This is when the value which is going to go into R3 is actually available within the processor, end of cycle 4. When is the value required by the subtract instruction? Unfortunately, the value is required by the subtract instruction at the beginning of cycle 4, and therefore there's no possibility of using bypassing. Bypassing can be used whenever there is a forward arrow in time. It cannot be used when there is a backward arrow in time. One cannot bypass a value into the past. Therefore, the very fact that this arrow is moving back tells us that this is a situation where bypassing cannot solve the problem. So in general, bypassing sounds like a good idea and should be used by the processor designers, pipeline processor designers, whenever possible. But we now realize that there may be situations where, because of when the desired result is produced within the pipeline, the designers realize that a value cannot be bypassed or forwarded appropriately. And then the question is, what can be done in such a scenario? Is it still necessary to delay or stall the instruction, in this case the subtract instruction? We note that if we had delayed the subtract instruction by 1 cycle, what would happen? Well, let me ask that in a slightly different way. If we consider the OR instruction which follows the subtract instruction, and it also is using R3 as a source, so it too is dependent on the load word instruction, then the normal course of events, so we are postponing discussion about the subtract instruction for the moment, we just consider the OR instruction. So it would have been instruction fetched, and then it would have been decoded, and its operands would have been fetched, again too early. But the question is, could bypassing have been used to satisfy the requirements of the OR instruction? And we notice that the OR instruction requires the value at the ALU input, the value which is going to go into R3. It requires the value to be in the ALU input at the beginning of cycle 5, and the value is available at somewhere in the pipeline at the end of cycle 4. Therefore, this is a forward arrow, and therefore that problem can be solved by bypassing. Therefore, the OR instruction requirements can be satisfied by bypassing. Unfortunately, the subtract instruction requirements cannot be satisfied by bypassing. Therefore, we suspect that in an implementation of a processor using this idea, we would see bypass paths in connection with the load word instruction. In other words, a bypass path from the LMD register into the ALU inputs, but that is essentially to cater to the instruction, not the instruction following the load word instruction, but the instruction which is after the instruction following the load word instruction. What then can be done for the instruction following the load word instruction? Okay, now this is a situation where forwarding or bypassing was taking us part of the way to a acceptable solution. An acceptable solution is one where there is no time penalty at all. But in this case, it looks like some kind of a time penalty is unavoidable. In other words, it will be necessary to delay the instruction by at least one cycle, the subtract instruction in our example. But there may be a better way to view this problem, and that is maybe to refer to the solution, which I'll call the load delay slot. And this may look like a familiar term, but let me first just define the load delay slot as an idea where we build the hardware to assume that an instruction that uses a load value is separated from the load instruction. In other words, we build the hardware in such a way that we assume that if there is a load instruction, then the instruction following the load instruction will not use the loaded value. In other words, we build the hardware to ignore this hazard. That's what this statement is saying. We build the hardware to assume that an instruction that uses a load value, such as the situation that we had, the situation that we had was the instruction that uses the load instruction is the subtract. That's the instruction that uses the load word. And to say that we build the hardware to assume that the subtract instruction is separated from the load instruction is to say that we are going to ignore this data hazard completely. And we have seen this kind of a word earlier. We saw it when we were looking at notes, interesting notes from the MIPS-1 instruction set architecture manual. You remember that at that time I had put up this slide. I'm now highlighting the upper half of the slide, where there was this interesting note. The note was, for load instructions, the loaded value might not be available in the destination register for use by the instruction immediately following the load. So, and this was labeled as, in our earlier slide, we had labeled this as the load delay slot, which is the same term that I'm using for it now. We now understand that what the load delay slot idea is, as far as an idea for solving the data hazards. It is an idea which basically says, build the hardware to ignore this kind of a data hazard. And in some sense, what's being done is to pass the data hazard as a warning to the programmer. Let the programmer know that every time a load instruction is used, the instruction following the load instruction is not guaranteed to find the loaded value within the destination register. And since the seed of doubt has been sowed in the mind of the programmer will ensure that the instructions are separated from each other. And as we've seen, if the instructions are separated from each other, such as the load word and the OR instruction, then bypassing can solve the problem. The problem was only with a situation where the instruction immediately following the load required the loaded value. Therefore, in some sense, the load delay slot is a solution to a data hazard problem in which the problem is avoided by just telling the programmer that this problem exists and assuming that the programmer, as I said in this slide, build the hardware to assume that an instruction that loses a load value is separated from the load instruction. And if the hardware makes this assumption, it's the programmer's responsibility to make sure that that this assumption now holds. And again, if the programmer reads the instruction set manual and understands that there's some doubt about the availability of the operand, he or she will write the program appropriately. Now the question which may be in your mind is, why is there any doubt? Why is this worded as might not be available? Why don't they just say will not be available or definitely will not be available? The answer to that question is a little bit more subtle. We should note that when we talked about this warning, we said that the warning was available in the MIPS-1 instruction set architecture manual. And the MIPS-1 instruction set architecture manual could be used as the basis for a hardware designer to build hardware for a MIPS-1 processor. Now, in building a MIPS-1 processor, there is no requirement that the person building the processor build a pipelined processor or build a processor in which there is a 5-stage pipeline with the kinds of problems that we have seen. One could have an implementation of the MIPS-1 instruction set architecture in which there is no pipelining, or in which this particular problem does not arise. And therefore, in general, when writing a program to run on a MIPS-1 processor, the user must be aware of the fact that for some implementations of the MIPS-1 processor, there may be a problem with this kind of an instruction occurrence. In others, it might not be there. But in general, the MIPS-1 instruction set architecture manual does not give guarantees about the availability of the loaded value to the following instruction. And therefore, the programmer in general could learn more about the particular processor that he or she is using, and if he or she finds out that this is not a processor in which this is a hazardous situation, could actually choose to write the instructions in a more aggressive way. Hence, the might not be available. This is just a statement of no guarantee coming from the instruction set architecture manual side. Okay, so with this we've seen 3 solutions to the data hazard problem. Let me just quickly remind you, there's interlocks, where there's a special piece of hardware which compares the source and destination operand fields of instructions and determines whether dependent instructions have to be stalled, prevented from progressing to the pipeline. That would result in loss of performance. There would be some cycles in which no instruction was completing. A nicer idea was forwarding or bypassing, where a result could be provided from wherever it was available in the processor, such as the ALU output, to wherever it is needed in the processor, such as the ALU input, making it unnecessary for the instructions to communicate data from producer to consumer through a register. It gets bypassed or short-circuited from the point of production to the point of consumption. And the idea of the load delay slot, where the problem of the data hazard could be sent, sort of just transferred to the programmer. Okay, now one other solution to the data hazard problem, which we are currently looking at, is a technique called instruction scheduling. We have seen the term scheduling before when we talked about the scheduling of processes. And scheduling of processes was the decision made by part of the operating system about which process should run next, which process should be in the running state next. Instruction scheduling, we would guess, has to do with the order in which the instructions should be executed. Just like process scheduling was about the order in which processes should be running, instruction scheduling must have to do with the order in which instructions should be executed. Right? So the idea of instruction scheduling then must be that if you're given a program, that maybe you could change the order of the instructions so that dependent instructions are far enough apart. And therefore, for example, in our example of the load word instruction and the subtract instruction, if I could find a way to change the order of the instructions, if previously the load word instruction was immediately followed by the subtract instruction, if I could reorder the instructions, change the order in which the instructions are present in the program, for example, then I might be able to diffuse the data hazard situation. Hence, the idea of instruction scheduling as a solution to the data hazard problem. Now, the reordering of instructions could be done at 2 points in time. It could be done either by the compiler, in other words, well before the program ever runs, and in that case, we would call the instruction scheduling static instruction scheduling, since the reordering of the instructions is done statically one time before the program is running. As an alternative, the reordering of the instructions could be done by the hardware when the program is running, and this is what is known as dynamic instruction scheduling. I won't be commenting on dynamic instruction scheduling in this particular course. I'll just give you a general idea about what dynamic instruction scheduling might be like. Now, the general idea here is that there is the pipeline processor. It has different stages. And the instructions proceed from one stage through the other in getting executed. But there may be some point in the pipeline at which a data hazardous situation might be identified, and it might be advantageous to change the order in which the instructions are executed. And therefore, if one could build a processor which could allow the instructions to proceed through the pipeline in their normal order until that point in time, and subsequently keep track of all the instructions which could be allowed to run next and pick them one by one in order to proceed through the pipeline. So over here we have some kind of a pool of instructions which have been gathered after having been fetched and decoded. Then the dynamic instruction scheduler would pick instructions from that pool, possibly one by one, and allow them to go through the pipeline. So potentially very sophisticated piece of hardware which would dynamically reorder the instructions. And many processors today have dynamic instruction scheduling. But we will try to understand the idea of instruction reordering or instruction scheduling by looking at a static example. So again, just to summarize that, many processors today do the reordering of instructions dynamically. In other words, it is done by the hardware and the programmer doesn't have to worry about it, and the compiler doesn't have to worry about it much either. But to understand how the reordering of instructions might be advantageous from the perspective of data hazards, we will look at an example from the side of static instruction scheduling. In other words, what could be done inside a compiler before a program runs, when a program is being compiled, to handle potential data hazards. In order to do this, I'll use an example. So the general idea is that we will try to reorder the instructions of the program in order to eliminate data hazards. But one could think of the objective of static instruction scheduling more aggressively. One could actually say that by eliminating data hazards, we are potentially reducing the amount of time to execute the program, because we may be eliminating many stall cycles, many situations where an instruction could not complete, many cycles in which an instruction could not complete. And with a little bit of thought, maybe the compiler could be used to analyze sequences of instructions and do reordering to come up with a sequence of instructions which results in best possible program execution time. So that may be a generalization of the objective of static instruction scheduling. Now, very clearly, when we talk about reordering instructions, for example, I have a program which has, let's say, 3 instructions. Reordering the instructions statically means changing the order of the instructions. In other words, it could be that I change the program to read, by reordering, I change the program to read I1, I3, I2. The program was originally I1, I2, I3, the sequence of instructions. I changed it by reordering into I1, I3, I2. In other words, I have reordered instructions 2 and 3. So under what conditions can I reorder 2 instructions? Very clearly, the reordering must not change the meaning of the program. If by reordering the instructions you cause the program to do something different, then that reordering cannot be viewed as being correct. So for a start, we must do only reorderings that are safe. And here's a simple example of 2 instructions. Here's an add instruction followed by a subtract instruction. You'll notice that the add instruction has as its destination R1, sources are R2 and R3. The subtract instruction has as its destination R2, sources are R4 and R5. And I may ask myself the question, can I reorder these 2 instructions? And with a little bit of thought, I realized that if I reordered these 2 instructions, the result would be that the subtract instruction would come before the add instruction. The subtract instruction has as its destination R2, and if you look carefully, you'll notice that the add instruction has as its source register R2. Therefore, if I were to rearrange these 2 instructions, I change the order of the add and the subtract, I come up with this sequence of instructions. And in this sequence of instructions, you'll notice that the add instruction and the subtract instruction have a data dependence between them, which was not actually the case in the previous sequence of instructions, in that the previous sequence of instructions, the add instruction was using R2 as its source, reading the value generated in R2 by some previous instruction, and the subtract instruction was not using any value generated by the add instruction. In other words, the subtract instruction was apparently independent of the add instruction. But when I rearrange these 2 instructions, I cause the add instruction to become dependent on the subtract instruction. And therefore, reordering these 2 instructions would not be safe. And therefore, in talking about instruction reordering, instruction scheduling, one must look at these kinds of scenarios. And just to allow our terminology to be consistent, I would note that in the sequence of these 2 instructions prior to the attempted reordering, you will notice that what these two instructions have in common is that there is a register which is used by both of them. And the first instruction is used as a source, and the second instruction is used as a destination, as a result of which it's not safe to just reorder these two instructions. On the other hand, if there had been a series of two instructions, here I've written an example with add R1, R2, R3. The second instruction is subtract R6, R2, R8. Here once again, these two instructions have R2 in common, but looking at it carefully, I realize that both of them are using R2 as a source, and therefore by changing the order of these two instructions, the meaning of the program will not change as far as these two instructions are concerned. Therefore, these two instructions can be safely reordered. These two instructions cannot be safely reordered. And we must understand that the relationship between these two instructions is a dependency of some kind. It's a dependency where there is a read followed by a read of R2 followed by a write of R2, as a result of which the reordering should not be considered as safe. Right, so short of these kinds of dependencies between instructions, it looks like instructions in many situations can be reordered, but that the compiler, in doing static instruction scheduling, will have to do this checking to make sure that instructions, which it is pairs of instructions which it is thinking of reordering, are in fact safe to reorder. Right, so the kinds of scenarios that we've seen here can be looked at. There are only a few possible scenarios. There's one where the data hazard that we saw was a situation where there was the add instruction was writing or using as a destination register R3 in that example, and the subtract instruction was using as a source. So the different possibilities could be analyzed by the compiler in order to determine what reorderings are safe. And we will continue with our discussion of the different techniques for handling data hazards in the lecture that follows. We'll start off with closing this discussion of static instruction scheduling. We'll look at a specific code example and look at in what ways a compiler could reorder the instructions of that code example in order not only to eliminate data hazards, but also conceivably to improve the execution time of the program containing that code example. Thank you.